Welcome! This is the next in my series of videos about understanding space weather. This one's about plasmas. Plasmas are very important in space physics. They're often mentioned, but they're poorly understood, and I'm hoping to change that a little bit with this video. Most people consider that there are three states of matter. There are solids, liquids, and gases. However, there are actually four states of matter, the fourth state being called plasmas. And plasmas are important because they make up 99.99% of the known universe. So how do these four states of matter differ from one another? In the solid phase, these are densely packed with strong bonds and incompressible. If you increase the temperature or energy of the system, they could turn into a liquid, which makes it loosely packed, weakens the bonds, and but is still incompressible. Gases, on the other hand, are very low density, have no particular bonds, and are compressible. Now, at first blush, plasmas would seem to be similar. They're low density, but they're charged, so they're a good conductor, and they're compressible. The other phases of matter may or may not be conductors. Some solids are very good conductors, while others are not. Some liquids are good conductors, while others are not. For example, pure water is not a good conductor, whereas if you add a salt of any sort or an impurity of any sort, it becomes an exceedingly good conductor. Gases are not particularly good conductors. So what are the properties of plasmas? First of all, they're electrically neutral, which means there's as many positive particles as there are negative particles within the plasma. The negative particles are generally electrons. Plasmas are generally low density. There are a few instances where they're high density, such as the core of stars, but most of the plasmas we see are very low density. When you move a plasma, you're effectively moving charge, which is equivalent to an electric current, and when you do that, you can create magnetic fields. So plasmas themselves are affected by the presence of currents and magnetic fields, and in fact feed back on those fields. So there's this very complicated set of interactions between plasmas, magnetic fields and electrical fields. And that's one of the reasons why plasmas are so poorly understood. Well, let's look at some examples of plasmas. Here I've got a plot of the temperature on the left against the density along the bottom. So let's take a look at a communal garden type of plasma, and that's a flame. The flames are hot enough that they ionize most gases, and so the gas within a flame can be considered to be a plasma. Another common one is a fluorescent light bulb. The gas in there is a plasma. It becomes charged and then starts to glow. Lightning is a plasma. It's a very dense plasma because it's in air, but nonetheless it is a plasma. The solar wind, the outflow of charged particles from the sun, is a plasma and interacts with our magnetic field on the Earth to produce aurora. Gaseous nebulae in deep space are plasmas because the local stars ionize the gases in the nebula, and so they become a plasma. The solar corona is an example of a plasma. At the time of eclipse, you can actually see the sun's magnetic field. Remember, the plasmas and magnetic fields interact. If the magnetic fields are strong enough, like they are on the sun, the plasma can't cross them, and so consequently the plasma outlines the magnetic fields on the sun, and that's hence you can see the magnetic field of the sun during an eclipse. And as I mentioned, the core of a star is also a type of plasma, but it's very, very dense. There are different types of plasma. One of the ways of differentiating between them is the degree of ionization. You can have a fully ionized plasma, which means that all the particles are charged within that plasma, i.e. it's hot enough that at least one electron has been pulled off of the individual atoms, and in some cases all of the electrons have been pulled off those atoms, and you're just left with a soup of protons and electrons. But you can also have partially ionized plasmas where the lowest percentage is 1%, and the example of that is in the upper atmosphere of the Earth, where there's a transition between fully ionized plasma in the magnetosphere and the neutral atmosphere. The layers between that are partially ionized. This is generally considered to be cold, but still can be many thousands of degrees. One of the interesting aspects of a plasma is that the electron temperature is not necessarily equal to the ion temperature. Now, what do I mean by that? Well, first of all, our concept of temperature is basically meaningless in a low density plasma because temperature is based on the collision rates that we see in the gases. But in a plasma, generally they're so low density that there are very few, if any, collisions. So that concept of temperature doesn't exist. There's several ways of characterizing the temperature. One way you can characterize it by the degree of ionization. A plasma created at 1,000,000 degrees, say in the solar corona, as it moves away from the sun, will maintain the ionization state characteristic of 1,000,000 degrees because there's no collisions to make it return to a lower temperature. So if you look at the ionization state of the particles coming past us in the solar wind, particularly the heavier ions, you can see that the plasma was created in 1,000,000 degree temperature or below. Another way of characterizing temperature is by the distribution of particles. Now, a group of particles at a particular temperature will have a distribution of velocities. A Maxwellian distribution it's called. Because electrons are much more mobile than ions, the electron temperature will be reached can be reached much sooner than the ion temperature. So the ion temperature and the electron temperature are not necessarily the same thing, and you'll often see a plasma characterized by its electron temperature or its ion temperature. And don't be confused if the two of them are different. As we heard before, particles in plasmas interact with both magnetic and electric fields, and when they do, they create waves called plasma waves. Now, each type of particle, the electrons and the ions, because of their different mass, interact differently from each other, and they also interact differently with electrostatic fields as opposed to magnetic fields. And there's a vast variety of interactions. I'll give you some examples here, but there are far more than I have time to go into here. With electrostatic fields, electrons produce oscillations, plasma oscillations, called Langmuir waves. How they're produced is that if when an electron is displaced within its plasma, because of the electrical neutrality of the plasma, that displacement will have a restoring force. It will try to pull it back to where it was before, and like a pendulum, when you pull it back, it will overshoot, so it will oscillate backwards and forwards around its position. That's what a Langmuir wave is. Ions react differently. They produce the equivalent of a sound wave, a traveling wave that goes along with the plasma, just like a sound wave would in air, and that's why it's called an ion acoustic wave. In magnetic fields, we get something different yet again. The electrons produce Whistler waves. Now, electrons can't cross magnetic fields, or charged particles in general can't cross a magnetic field, so they tend to spiral around them. In special circumstances, and this was discovered during the First World War with radio communications, they produce what's called a Whistler wave. There you get a wave that starts out of a particularly high frequency and slowly drops to a lower frequency, like that. And that's, you're seeing that plot here. That's a Whistler. Ions, on the other hand, produce a traveling wave that go along with the plasma, and that wave travels with the along the plasma at a particular speed. Those are called Alfvén waves, and those Alfvén waves are one of the ideas that people have had in the past as to how the corona is heated. The problem is you must dissipate them in the corona somehow, and that's always been a Achilles heel of that particular theory. So what do we conclude from all of this? First, plasmas are the most important phase of matter in the visible universe because it makes up 99.9% of the visible matter that we can see. Stars, nebulae, our upper atmosphere are all examples of plasmas. We have many technological uses for plasmas, from lighting to energy production. Unfortunately, they are misunderstood by many of us. These first few videos have been trying to explain some of the terms I used in the first paper of my series Understanding Space Weather that have been published in bulletins of the American Meteorological Society. The first paper is entitled The Sun as a Variable Star, and it was by myself, Dr. Julia Saba and Dr. Teresa Cuchera. You can see a copy of that online for free at the URL listed below. Next time we're going to go on to the terms used in paper 2, and I'm going to start off by talking about flares. Until next time, stay safe. Goodbye.